Good morning, my YouTube viewers. In this video, what we're going to talk about is Pearson's correlation coefficient, which is the linear relationship between two continuous values, and it gives you a range of -1 to +1. If it's a -1, it means it's a perfect negative correlation, and if it's a +1, it's a perfect positive correlation. And if it's a 0, then there's no correlation at all. So Pearson's correlation coefficient is a measure of association. So measures of association refers to statistical techniques used to quantify the strength and direction of the relationship between two variables. It is a fundamental concept in statistics, helping to determine whether and how strongly variables are related. This measure is widely used in fields like sociology, economics, biology, and more. So on Pearson's correlation coefficient, in order to prove this function, what we're going to do is we're going to write a program in Python to do that. And then so in order to write the program in Python, what we're going to need is we're going to need to import a library. So we're getting from scipy.stats, we're going to import Pearson R. So scipy is Python's scientific library. Stats is a statistical module within scipy. And Pearson R is the function in the stats module. So what we're going to do is we're going to create some synthetic data. So our x variable, which is our independent variable, is a list of numbers of 10, 20, 30, 40, 50. And our y variable, which is the dependent variable, is a list of numbers 5, 21, 27, 33, and 39. And now what we're going to do is we're going to calculate the Pearson's correlation coefficient and p-value. So r comma p-value equals Pearson r x comma y. So we're going to display the results. So we're going to display the x, y, Pearson's correlation coefficient, and the p-value. And we're going to So we've got our answer. So we've got our data X is the 10, 20, 30, 40, 50. Data Y is 5, 21, 27, 33, 39. X is your independent variable and Y is your dependent variable. We've got our Pearson's correlation coefficient is 0.97. That indicates that it's a near perfect positive correlation. Got a p-value of 0.006, so your p-value is less than 0.05. And if your p-value is less than 0.05, that means that the null hypothesis is rejected and the alternate hypothesis is accepted. And so basically what happens is the null hypothesis would be there is no significant difference between the two samples of data. And the alternate hypothesis is there is a significant difference between the two samples of data. And your p-value is a probability. And so since the p-value is less than 0.05, it means you have to accept the alternate hypothesis. And the alternate hypothesis, it means that there is a significant difference between the two values of data. So we come over here and we printed the results, and then we're going to interpret the result. If abs, that's the absolute value of r, is 1, it's a perfect linear relationship. If the absolute value, if the absolute value of r is greater than 0.7, it's a strong linear relationship, and that's what it was, because it was, I think, the 0.97, so that meant it was a strong linear relationship. Else if it was greater than 0.05, it was a moderate linear relationship. Else, if it was greater than 0.3, it's a weak linear relationship. Else, it was no significant linear relationship. And so, as we can see right here, with the answers we've got, it's a strong linear relationship because it was 0.97, and it was between 0.7 and 1, so you had a strong linear relationship. I would say that it was a near perfect linear relationship. So that concludes this video on the Pearson's correlation coefficient. The next video we'll be working on is the Spearman's rank coefficient, which is a different type of measure of association, and I hope you decide to watch it.